Hello class, and welcome back yet again. Okay, so the last one we had an introduction to digital circuits and to the various elementary digital logic components. In this example here, we're going to do it over two parts. So part one, we're going to take some functional expression that's going to represent the digital schematic for a new toaster. And what we'll do is we'll apply the Boolean algebra identities that are here. So we'll look through the functional expression in a minute, and we'll use these identities to reduce down that circuit. When we reduce down that circuit, the big question you have to ask yourself is, what does that mean? And the real meaning behind that is we save money, it becomes more efficient, and so on and so on. If you look back through your notes, you'll get many more examples. So I suppose we'll get started and we'll look at that expression. So I will be using these Boolean algebra identities, and what I'll do is I will tell you, or I'll show you the identity as I'm reducing down that circuit. You should become familiar with the Boolean algebra identities and be able to apply them to any functional expression. They will be supplied on the exam. Okay, so what we said was that we're going to look at the digital schematic of a toaster that automatically wakes you up in the morning with some toast. Now this is represented as a functional expression, so we can say that f, which is the functional, is equal to x, y, in brackets we've got the complement of y, or not y, or x, z, y, or x, z, y. So using our knowledge of the Boolean algebra, we can reduce this logical expression down. In part two, what we will do is we will draw this expression and we will see what it looks like in terms of a digital component diagram. So the first thing we're going to do is use the distribution law, and we're going to multiply this xy across the brackets. So that'll simply give us x, y by the complement of y, or x, y by x, z, y, or x, z, y. So we've used the distribution law to multiply this in. Now the next thing we're going to have to look at is, if we look here, we have y by its complement, and if you look on the identities, y by its complement yields a 0. So we multiply it in, so we have x by a 0, or x and a 0. Or, now if we look here, we've got an x ANDed with an x, because of association the ordering here doesn't matter, and a y ANDed with another y. So in other words, you look at the identities, if you have x ANDed with itself, well, it simply breaks down to being equal to x. So if we apply that to the x's and the y's, we simply reduce down and we get x, y, z. And we follow on the rest of the expression, we have or x, y, z. Now in the Boolean identities as well, if we have x ANDed with a 0, well, that's going to just yield a 0. So we can eliminate this term. So we end up with x, y, z, or x, y, z, which is simply equal to x, y, z, because of the identity x or x is equal to x. So this is our new expression. And what we're saying is that from a digital perspective, x, y, z is the exact same as this expression up here. Okay, so how we'll prove this is we'll look at the truth tables associated with this functional expression. Okay, so we'll start off this and we'll build it up slowly. Okay, so if we think about it, we've got an x and we've got a y, we've got a z. So we've got three components in our truth table: x, y, and z. Now if we think about how many elements do we have, so we've got 3 characters, so we have 2 to the power of 3 options, which will give us 8 options. Just like if we had n elements here, well then we would have 2 to the power of n options. So we have 8 options for the various on-off switches for each of these elements or each of these components. We'll start off with Z, and we just write down the combination, yeah? So true, false. So they're the only options we have, so we repeat this down until we have 8. True, false, true, false, true, and false. So now we've got 1, 2, 3, 4, 5, 6, 7, 8. For the second element in, we go in pairs, so we say 2 trues followed by 2 falses, followed by 2 trues, followed by 2 falses. And the last one in, we have 4 trues followed by 4 falses. And what we'll do here is we'll just draw out a little line. Just so we don't lose track of where we're going. So remember, the truth table shows you at any given stage the actual output of the circuit or the expression. And what we need to prove here is we need to prove that XYZ is actually equivalent to this full expression. And if we prove that, we can substitute this expression here for this expression and still get the same functionality out for our automatic toaster. So what we need to do now is we need to come up with this final expression. So what we'll do is we'll step through in an iterative process and we'll work out the elements for each of those subcomponents until we build up a full expression. So the first thing we look at is this not y, and we'll draw out the truth table for not y. So we see that y is true, true, false, false. So if we say not y, well, it's simply going to be false, false, true, true, false, false, true, and true. So that's our not y done. So now we'll bridge up a couple of the other components. So what we need to do is we need to have a look at this expression here. So we have not y or x, y, z. So let's look at x, y, z. So x, y, z, and what we need to do is this is ANDing x, y, and a z, so we know that true and true and true is true, but we also know that false ANDed with anything from our earlier examples is equal to false. So if we see here, we've got a false here within these 3 categories, so that automatically means the whole expression is going to be false. We have a false on the next line, the false on the next line, and then if we look at x, the last 4 are all false, so we say false and anything else is going to give us a false, and that applies to the last 4 rows. So that's that expression there. So inside this bracket up here we've got not y or x, y, z. Okay, so we have not y or x, y, z. So we look at this expression here now, yeah? So we say false or true is true, false or false is false, true or false is true, true or false is true, false or false is false, false or false is false, true or false is true, and true or false is true. So we've done the inside of the brackets now. Now this whole element inside the brackets is being ANDed with the xy, so we need to do up a little truth table for x ANDed with y. So we say true and true is true, we say true and true is true, we say true and false is false, we say true and false is false, and then false, the last 4 ANDed with anything is going to be false. So now we've got xy and we've this component, so let's build the full thing. Xy ANDed with not y or x, z, y. Okay, so we say true and true is true, false and true is false, true and false is false, true and false is false, and then we've 4 falses, and about anything gives us 4 falses. Now the last expression that we need to look at is this full expression. Okay, so what we have is we've got x and with y and with not y or xzy, and then we need to or that with xzy. So we'll call this full expression f, and when we look at f, we simply or xzy with this column here. So we have xzy, which is true or true, gives us true. And now we have falses all the way down here. So every element here in these rows or in this column are falses, and it's similarly down here as well. So false or false will always yield a false. So what we need to look at now is this is a full expression. So this expression is represented as, or the output is represented as true, false, 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 false. And what we're saying is that our expression, this full expression here, is equivalent or equal to the expression of x, y, and z. But if we look at our table here, we have a table already for x, y, and z, and it can be clearly seen that both of these are the exact same output. In other words, the truth table are identical, which means that this reduced component here that we got by reducing using Boolean algebra is equivalent to the initial expression associated with the digital toaster. And because these are true, we're all finished. We draw a little happy face.